So in this chapter, what we're going to see, what we're going to learn, is how to do some calculations associated with a chemical reaction. If given a certain amount of a reactant, how much product will form, that kind of thing. And so we're going to do some math, and it's math that's actually we've learned this math before, dimensional analysis. That's the at the heart of what we're dealing with here. And we could just jump straight into the calculations. I don't want to do that yet. I need to introduce a concept. I need to introduce something called the mole, and we'll get to the mole in just a minute. Let's just think about what a chemical reaction is telling us. So this real simple kind of setup: one sodium cation, one chloride anion is going to form one molecule of the sodium chloride salt. Let's just say, let's put that. So we say, well, not that. That's a little bigger. There we go. So what did I say? I said one ion here plus one ion is going to yield one molecule. That's physically what's happening when these two things. That's physically what this reaction is trying to describe. Well, there's a problem with this. 1, 2, 3, any small number of a single ion or a single molecule, you're talking about a mass that, somewhere in the range of, give or take, 10 to the minus 27 kilograms. It's something that we can, as humans, have technology that allow us to record masses that low, but we don't have something like a balance that we can just go in the laboratory and weigh out a single thing. Okay, so what we need to do is we need to ramp up the number of ions and molecules that we're talking about with this particular reaction. Imagine this: what if I said 12 ions and 12 ions to produce 12 molecules? All right, that's a little bit bigger. Fine, it's still in that range. And the reason why I mentioned 12 is we're talking about instead of saying 12, I could say a dozen. 1 dozen this, 1 dozen that yields 1 dozen that. All right. So, right, we have these phrases that we can use to represent some amount. Well, in chemistry, it turns out if we use this amount, and I'll get into a little bit about where this number comes from, but even in a second video. But right now, again, I just want to sort of get everything in front of us so we can take a look at it. Right? I can ramp up it to any sort of arbitrary number. That's kind of what this is. It's kind of an arbitrary number. And it's referred to, the actual term for this is Avogadro's number. Let me just go ahead and put that out. Avogadro's number. Italian chemist, early to mid 1800s, worked with gases a lot, and he was concerned about. He wanted to know about the number of atoms and molecules that he was working with. And basically, and we'll see a little bit about this in the gas law chapter. Basically, Avogadro, with working with gases, he made a statement essentially saying that if I have two different gases, let's say, in front of me, and they're the same pressure, same temperature, same volume, then I'm going to have the same number of molecules or atoms in that gas. And that's generally true. And it's something we'll talk about in the gas law chapter. But Avogadro's research and contribution to our understanding of gas laws and molecules and atoms, we give him this honor of naming this particular number after him. So, to my knowledge, Avogadro did not come up with this number. Could be wrong, but chemistry history is a hobby of mine, so I'm not an expert in it. But from what I've gathered, he did not come up with this number. We just named it after him. Okay, so what's the big deal? Well, all right, couple things. One, if we have this number of ions, now we're in the gram range, which is very convenient. That's something that we can easily measure in the laboratory. And if I had, and let's just look at this number here, if I had this many number of molecules of sodium chloride, I can easily, physically see that in the laboratory. That's how much it would look. This is probably, I don't know, a 50 milliliter beaker is what that looks like. That's a lot of sodium chloride to work with. That's something very easy that I can measure out. And then if you're talking about copper or sulfur or any of these other compounds, if I measure out that number of those molecules or atoms, notice that in each case it's quite a bit. It's something that's very easy for us to work with. And what we're going to see actually is that based on our knowledge here, we can use the information on this guy to relate back to this number as well. Okay. Now, before I get too far ahead of myself, let me just say this. When we're talking about a chemical reaction here, and we see that 1 and the 1 and the 1, or 2 or 3, whatever that coefficient in front is, what does it match with? It matches with this. That's okay. It doesn't match with any of these other ones. Well, what we're going to do is we're going to actually introduce now our concept of the mole. And what is a mole? 1 mole of sodium ions. 1 mole of chloride ions are going to yield 1 mole of sodium chloride molecules. So yeah, there's 2 of those embedded within there, but together they make 1 molecule. And so the ratio is a 1 to 1 to 1, just like we see up here. And that 1 mole represents that number of ions or atoms or molecules. And so that's the link between the 2 concepts. Just like 12 ions equals 1 dozen, or 12 bagels equals 1 dozen. It's just, or 1 ream of paper represents 500 sheets of paper. So it's just a relationship between really 2 different measurement units, if you will, counting individual things versus some group of things. And this becomes very useful for us. Okay, how useful is this going to be? Well, as it turns out, now if I was to weigh, and I'm going to see if I remember these numbers, 22.99 grams, and this one, I know this one's 35.45 grams. And if you add these 2 together, it's 50, oh boy, hang on, let me get my notes or something. Okay, it is 58.44. Great. So now, if I, again, these things, Avogadro's number, 1 mole, and this mass that I'm writing out for each one, they're all related to each other. Again, if I go into the laboratory and I weigh out exactly 58.44 grams of sodium chloride, I am going to have that many number of molecules, approximately, of sodium chloride, and I'm going to call that 1 mole of that substance. Well, where do these numbers come from? Well, I know these numbers because that's what's on the periodic table. The 22.99 for the sodium's coming from there, chlorines coming from there. Add them together, that gives me my sodium chloride. So we've been seeing, we've used the periodic table quite a bit now. We learned how to calculate this in a previous chapter, and now we're applying it to this concept of what's called stoichiometry. We'll see the term later, but stoichiometry just means a measurement of a system of measurements, measurements of amounts, basically. If you break down like the Latin or Greek base words in there. All right. So all of these masses here, and the other ones that I'm going to use, are going to be those 3. Yeah, and let's just continue with this. So all of these masses represent 1 mole of a sample. Okay, that's fine. That's the modern interpretation of what a mole means. I want to sort of go back a little bit, step back a bit from this, and just give the history of this is more than what we really need to do, right? This is not a history of science class, but I found this useful when I was learning about the mole. And so let me just share this little bits of data with you about where does the mole, and this unit. This unit is very useful for us in just a few minutes or so, and for the rest of our Gen Chem 1 chemistry career, however long you might be in a chemistry class. Okay, so relative mass. We're talking 1800s. So we're talking Dalton, Avogadro, even Mendeleev. If you look back at that time period, you're not going to see, when we think about all of these numbers on the periodic table, I mean, these numbers, we've been talking about atomic mass units, which, is at approximately 10 to the minus 27 kilograms. We're talking about some kind of mass for these elements. It's a very specific unit, both of these. That's not what they were working with. They had relative masses. They knew that they let hydrogen be the standard, hydrogen be one of whatever unit that is. They didn't know how big, they didn't know how small. I mean, they knew it's small, but they had no relative sense about, how small is this thing? But they knew the relative sizes of these different elements. Hydrogen, again, would be given the standard of 1. And then 12, carbon is 12 times as heavier than hydrogen. Iron is 56 times as heavy as hydrogen. And they use that. And if you do that, I mean, that's just really basically the number. I mean, now we have a much more precise measurement of that relationship. But that's basically the bottom number on each of those elements. And it works just fine. But again, at some point along the way, they wanted to know this. They wanted to know, well, how many of something are we talking about in the context of some mass that we can deal with? All right? And again, not getting into the weeds of the history here. Basically, think of it this way. They said, okay, we have these relative masses. We're going to stick with these relative masses. And we're going to say, okay, let's use a unit. Again, I think a professor of history of science might cringe at the way I'm doing this. But think about it this way. So we have these relative masses, and we say, okay, well, let's just use a unit. We'll say, well, what if we have 1 gram of this and 12 grams and 56 grams? And basically what we're doing is just converting the relative relationships by mass, I mean, that's what it was, to a particular unit. And lo and behold, what we find is that when we do that, when they did that, that's what they saw. They saw that, oh, well, we have this number of this number. Again, this is now Avogadro's number, and just sort of get it out of the way. N sub A is the way that's going to be expressed. And then chemist says, okay, so we have this relationship, and so now it's all we can interpret these bottom numbers as meaning a certain number of atoms. And what we found is that it is very convenient to then go one more step further, and establish that as equaling that 1 mole of something. Again, when you see a mole, that's just like a chemist's dozen. We're trying to ramp up the number in such a way to where we get a mass that's convenient. And what we have now, well, now I'll put this in red because it's so important. This is basically a conversion factor. That's a conversion factor that allows us to flip-flop between number of grams of something to the number of moles of something. Why is that relevant? Well, getting back to our chemical equation here, think about what did that 1 mean? Did that 1 mean mass? No. It did not mean mass. These numbers here just emphasize that does not. I'm not saying 1 gram plus 1 gram equals 1 gram. No, it's 22.99 grams. We can physically weigh this out and track it down and all that. But notice that we can say 1 mole, 1 mole, and 1 mole. That does correspond to that initial concept of 1, 1, and 1 as laid out by these chemical equations. So whenever we see these there's a term, molar coefficient. It's been on the tip of my tongue this whole time that I've been talking about this. Coefficient. These are the numbers that we're going to use to allow us to make predictions and study chemical equations. And again, we have a link between grams and the mole. It is the atomic mass, or later on we'll see molar mass. Now, what is more traditional here? What's more traditional? I'll just keep it in red, and I'll just use the number that's on the periodic table itself. And I don't have room for the iron, so I'll just stop here. So notice this is the proper abbreviation. You just drop the E to go from the word mole to the abbreviated term mole. And we say it's 1.01 grams per mole. Grams equals 1 mole. And so it's just converting our conversion factor, if you will, into a derived unit. That's what we have here. And it represents this atomic mass for these individual atoms. And again, there'll be something later called a molar mass that we'll use to talk about molecules in the same way. Okay, now I think I've said enough about mole and the relationship to grams and all that. If you're doing the calculations, let's see how long this video is. Okay. So, if you're doing the calculations and you get bogged down, and maybe you can do the plugging and chugging fine and all that, and you sort of forget what the mole means, watch the video again. You're not going to get an essay question about what is the mole or the history of the mole, but again, what I did here, it's what helped me to understand what that mole was. And then what's more important here is how it links back to these equations and the mass. Because without at least understanding that a little bit, what you're doing is you're just going through the motions of doing calculations. And to get a better feel for what's actually happening, you need a little bit of an understanding of this concept here, which hopefully helped a little bit. Okay, that's enough. Thanks.